Nothing pleases me, nothing pleases me, nothing pleases me but you. Oh, that was a takeout from a song by the band called the Layabouts. Okay, let's get on to the serious stuff, the mystery of nothingness. Because space does not seem to allow for its existence. Vacuum is nowhere to be seen. So let us explore. Meet Lepicus and Democritus. They proposed atomism, the idea that the universe is composed of tiny, indivisible solid particles, atoms, moving through infinite empty space. For them, the void was a necessity. Without empty space, how could atoms move? You'll notice that the two statues, they look remarkably similar. They could be twins. I suppose that's because we really don't know what they look like, so these are sculptural interpretations. You see a lot of that with famous people from ancient Greece. So on the Leucippus and Democritus clock, the dial stands at nothing. So here's a statue of a guy who looks remarkably like the other two statues we saw. That's because we don't really know what Aristotle looked like. Well, Aristotle, whose philosophy dominated Western thought for 2 millennia, rejected the vacuum. He argued the physical universe was a plenum, in other words, completely full. Why? He had several arguments, but they boiled down to one principle: nature abhors a vacuum. You've got to keep in mind that these three were probably not the first people to consider and debate and talk about this. It probably goes back to the Egyptians, probably goes back much further. Probably hunter gatherers sat around and looked up at the stars and wondered about the idea of somethingness and nothingness. But getting back to Aristotle, he observed phenomena that seem to support this. If you put your finger over a straw and pull it out of water, the water doesn't fall out. Why? Aristotle said it's because if the water fell, it would leave nothing behind, and nature will not permit this. Water is pushed back or held up to prevent the vacuum. Now, what I like about this is that Aristotle is using observational evidence in order to support his theory. So, this seemed like a pretty cool idea and lasted for a very long time. The dial had swung from nothing to something. So, we're left with Aristotle for many, many moons, and we go through the fading of the Greek civilization. Up comes the Roman civilization, and they really don't understand any more than what Aristotle is saying. It appears they could not grasp the concept of osmosis, a means of transporting water. So, hence the viaducts. And that was the main way that water was transported. And that concept remained for a very, very long time. So, for centuries, this vacuum, no vacuum, wasn't just a physics problem, it was a philosophical and theological absolute. The argument goes that if God is everywhere and nothing is the absence of God, then a true vacuum would be a space without God, a mathematical or physical impossibility. It is also worth noting that the era from the classical Greeks up through the Dark Ages into the Middle Ages, nothing really new happens in terms of physics and astronomy. And it's only when we get to the Renaissance that things start to change. I love this image done by Michelangelo in the Sistine Chapel of God reaching out to man and man reaching out to God. It so well encompasses this era, this sort of dark age between the ancient Greeks in the beginning of a Renaissance. And it's so extraordinary that when the Renaissance arrived, we see Galileo noticing things about nothing and pressure, and also looking at the stars. It's quite extraordinary, really. The philosophical blockade, Aristotle's nothingness, not being able to exist, stood for almost 2,000 years. And the cracks only appeared during the Renaissance, driven not by philosophers, but by engineers trying to solve a practical problem: pumping water out of mines. They found that no matter how powerful their pump, they could not lift the water higher than about 33 feet. Galileo, he studied this and famously quipped that perhaps nature's horror vacui was finite. She only abhorred a vacuum up to 10 meters. It was a clever answer, but not an explanation. The breakthrough came from Galileo's student, Evangelista Torricelli, from 1643. He had a brilliant insight. What if the water isn't being pulled up by the fear of a vacuum, but is being pushed up by something external? Torricelli realized we live at the bottom of an ocean of air. This air has weight, and it pushes down on everything. Torricelli created the first artificial vacuum. He filled a long glass tube with mercury, which was 13 times denser than water, sealed one end, and inverted it into a bowl of mercury. The mercury in the tube didn't empty. It fell to a certain height, about 30 inches, and stopped. The 30 inches of heavy mercury were perfectly balanced by the weight of the air pushing down on the surface of the bowl. And what was in the space above the mercury column? Nothing. No air, no matter. This space became known as the Torricellian vacuum. And for the first time, humans had created and proved a physical void. It is interesting to note that Torricelli was doing his experiments a short time after the work of Johannes Kepler and Tycho Brahe, who were instrumental in putting the sun in the center of the solar system, confirmed 100 years later in the work by Isaac Newton. Then, roughly 10 years later, along comes a German engineer and politician named Otto von Guericke. He decided to take this idea from a small glass tube to a spectacular public stage. So in 1654, he took two large copper hemispheres, fitted them perfectly together, and used a pump he designed, and it happened to be the world's first vacuum pump, to suck the air out from inside. Because the pressure inside was a near vacuum, the immense pressure of the atmosphere outside crushed the spheres together with hundreds of pounds of force. He hitched up 16 horses, 8 on each side, and they could not pull the hemispheres apart. The physical reality of the vacuum and the crushing weight of the ocean of air was undeniable. Aristotle was defeated by engineering. And so, between Torricelli and Guericke, the dial has swung again to the other side. The nothing reigns again. But now, science was accelerating. By the end of the 17th century, the debate had shifted. Science now accepted the physical vacuum, a region devoid of matter, but immediately a new, more subtle version of the horror vacui returned. This time, it was driven by the new science of light. Scientists understood light as a wave, and all known waves needed a medium to travel through. Water waves travel through water, sound waves travel through air. If a light wave travels through a vacuum of space, that vacuum must not truly be empty. It must contain a medium. They named this medium the luminiferous ether. It had to be magical substance, rigid enough to transmit light waves at an unimaginable speed, yet subtle enough to allow planets and stars to move through it without any drag. For the whole of the 19th century, physics was focused on finding the properties of the ether. The something was back. This particular part of the story culminates in 1887 with the famous Michelson-Morley experiment. If the Earth is moving through a sea of stationary ether, like a boat moving through water, there should be an ether wind. If you shoot light against the wind, it should travel slower than light shot with the wind. Michelson-Morley built an extremely sensitive instrument to measure the difference, and they measured nothing, no change. Speed of light was constant in all directions at all times. It was a catastrophe for the 19th century physics. If the ether wind didn't exist, the simple conclusion was the ether itself didn't exist. Light somehow traveled through truly empty space. The passive, dead, empty void was back, and it seemed to be the final answer. The needle had turned back to nothing. This view of vacuum as a passive nothing lasted exactly as long as classical physics. In the early 20th century, two revolutions destroyed the old order: general relativity by Einstein and quantum mechanics, Planck, Heisenberg, Schrödinger, Dirac, and others. Together, they utterly reinvented our definition of nothing. Let us start with general relativity. Einstein showed that space and time are fused into a single four-dimensional fabric called space-time. A vacuum, a space-time region with no matter and energy, isn't just empty, it has geometry. It can be flat, but near a massive object like a star, this nothing is warped, stretched, twisted. Gravity isn't a force. Gravity is the shape of this nothing. The vacuum itself has physical property, a curvature. So now we come to the quantum vacuum. Quantum vacuum field theory, that's our modern description of reality, teaches us that particles are just excitations. They're ripples, underlying fields. An electron is a localized peak in the electron field. A quark is a peak in the quark field. The vacuum state is not nothing, but rather all the fields with no ripples. But because of the uncertainty principle, these fields are vibrating slightly. These vibrations have just enough energy to spontaneously create pairs of particles, a real particle and its antimatter twin, like an electron and a positron. These virtual particles appear out of nothing, borrow energy from the future vacuum, and almost instantly collide and annihilate, returning the energy. The vacuum is not empty. It is a dynamic, roiling quantum phone of virtual particles constantly popping in and out of existence. Is this real? Yes, it is. We can measure the fields and their effects. The most famous accepted proof is the Casimir effect. If you take two perfectly flat, uncharged metal plates and place them extremely close together in a perfect vacuum, there is an attractive force pulling them together. Why? Because in the huge space outside the plates, every single possible wavelength of virtual particle can pop into existence. But in the tiny gap between the plates, only virtual particles with wavelengths that fit exactly in the gap, like a guitar string, are allowed. This means there are fewer virtual particles popping to existence between the plates than outside. The dynamic nothing outside pushes the plates together with measurable, predictable force. And so the needle has swung again, seemingly firmly into the something realm on our dial. All space, as we know it, is a fabric, and within that fabric, there is no such thing as nothing. So in the top hand left corner of the diagrams, imagine if you grabbed an arbitrary cubic meter of space in intergalactic space, the thinnest space we know of. In that cubic meter, you would see background radiation passing through, electrons whizzing through it from time to time, protons as well, dissociated electrons and protons are a plasma, and billions of neutrinos passing through that cubic meter as well. The lower left diagram is the Casimir effect, which we have already talked about. And on the right, this very busy area is the volume of space, which is the rarest space you can possibly imagine. And within this area, there are virtual particles coming to existence and then annihilating, a quantum foam. So, from the ancient Greeks until the present day, we have seen the needle swing from something to nothing repeatedly. Now that we have completed this historical battle between something and nothing, I'd like to delve into some intriguing natural phenomena that pertains to this subject. Observations that I would put under the heading, Nature does some strange things with empty cavities. Take this peculiar creature, for example. This is the amazing mantis shrimp. It has these large cudgels that it uses to hit its prey, and it does so faster than a bullet. At the moment of impact, a superhot cavity is created, which has the temperature hotter than the sun. Captured in the year 2000, this is a close-up of the Bastille Day solar flare, possibly the most powerful solar flare we have ever managed to record in such magnification. Notice how moments before the discharge, it writhes like a living, tightly bound slinky. With the speed of a flashbulb, the slinky explodes into blinding brightness that, when it reaches the Earth, will knock out several satellites with a pulse and create huge auroral lights in the north and southern polar hemispheres. Something similar to this has actually been replicated in laboratories. They call the phenomenon sonoluminescence. It was discovered that when you combine sound of particular frequencies with water in a round glass bottle, it creates a cavity bubble in the center which fluctuates and then suddenly bursts into a bright light with the temperature more than 3 times that of the solar surface. Many speculative papers have been written on the subject, one of which suggests that at the moment of creation, the temperature of the cavity drops below 4 degrees Kelvin, which is exceedingly close to absolute zero, a temperature that cannot exist within the space fabric. In this exceedingly slow motion film experiment, a gun is fired underwater and cavities occur. What is so extraordinary is that as the cavities collapse, it appears that sonoluminescence occurs. This filming was done in daylight, so you have to pay attention to see the brief flashes occurring. Cavitation is extremely corrosive. It can even chew through stainless steel, leaving the smooth surface severely pockmarked. Here is a discarded ship propeller that needed to be replaced as cavitation action had lowered its efficiency. The internal structure of lightning is still poorly understood. Even the higher speed cameras have yet to capture the structure between the electrons and protons that make up an electrical strike. The renowned plasma physicist Anthony Peratt speculated that the internal structure would be akin to the spiral electrons and protons in separate cants interacting and intertwining. The dynamic would not be unlike an ion pump in which fired electrons are created to sweep up remaining particles when attempting to create a hard vacuum. Taking it a step further, might it be possible that the lightning is stretching and compromising the fabric of space? And as the paper suggests in the sonoluminescence experiment, the core of the lightning drops in temperature, not to 4 degrees Kelvin, but all the way down to zero. That electrons and protons are flowing along a superconductor boundary. If this is so, it might be the solution to the mysterious and yet unsolved ignition problem, in which no viable mechanism has adequately explained how cloud to cloud lightning can reach from one to another across appreciable distances, despite the fact The clouds are an insulator. So, presuming for a moment that the fabric of space can be compromised, what are the implications on a universal level? Consider these four panels. The first one is just space. This is space. All space in the universe contains matter and radiation. There are no exceptions, much like we pointed out earlier in the presentation. The second one is this is hollow, a space with nothing in it, but it still has space in it. And the next one is this is empty, a volume with no space in it. This is subspace. It is a singularity. The volume within is unknowable. It contains no time, no temperature. And then finally, how does this impact space when such an object, such a cavity should appear? Well, subspace cavities cannot be directly observed. It is only the behavior of gravitationally imploding space that allow us to determine the existence of subspace. And that's a pretty good description of our sun. Okay, let's entertain the fantastical for just a little longer. Keeping in mind the idea of an absolute vacuum or a subspace, this temperature gradient summary of the solar interior using a photosphere and sunspot temperatures, if we continue a linear temperature drop, how far down until we reach absolute zero? On the lower part of the diagram, what you're seeing here is the sun limb. So you're looking across the horizon line of the sun, and in the center there's a sunspot. Now, the actual photosphere, which is the sun's atmosphere, is 5,000 degrees Celsius. The sunspot penumbra, that's where it starts to dip down, is 4,000 degrees. And when you get to the sunspot umbra, it's 3,000 degrees, and that's as far as we know anything can be seen. On the lower left here, you see a scale of the planet Earth in relation to the size of the sun. As you can see, it's quite small. So a comparison scale is about 12,742 kilometers. That's the diameter of the Earth. The depth point at which the temperature gradient reaches superconductivity is 11,759 kilometers. So that's sort of about most of the distance across the diameter of the Earth. So the point at which the temperature gradient reaches absolute zero is 12,187 kilometers. So that's about the size of our planet and maybe a little bit more. Surrounding that absence of space, that nothing, so seemingly impossible to obtain, the elements that make up that surrounding space fabric inevitably evoke a violent implosion reaction upon the cavitation. When we observe parallel, seemingly unassociated patterns of nature, are we not duty bound to ask if they have a common thread? Thank you for taking the time to watch my The Nothingness. I hope you enjoyed it as much as I enjoyed making it. Goodbye.